This is Chapter 9, Steady State Power Analysis, Sections 1 to 4. Our learning goals for these first four sections are to consider instantaneous power for the special case of steady-state sinusoids, average power, that is the power absorbed or supplied during one cycle, the maximum average power transfer when a circuit is in sinusoidal steady state, and then finally effective or so-called RMS, root mean square values, for the case of sinusoidal signals. Section 1, Instantaneous Power. Instantaneous power is the power provided to an impedance, which can be defined as P of t equals V of t, I of t, and the instantaneous means at any particular instance of time t. In a steady state AC analysis, the excitation voltage as shown V of t could be considered as V sub m, the amplitude, cosine omega t plus theta v, and as we've seen, omega of course is the radiant frequency, and theta sub v is the phase angle. For any arbitrary impedance z, as we've seen, the resulting current I of t is I sub m, the amplitude, cosine omega t, the same radiant frequency, omega, plus a new arbitrary phase angle, theta sub I, which is calculated by the value of the impedance at that particular radiant frequency, omega. The instantaneous power then is the product. P of t is equal to V sub m, I sub m, cosine omega t plus theta v, times cosine omega t plus theta I. Now we do know from trigonometric identities that cosine phi1 times cosine phi2 is equal to 1/2 the quantity cosine of the difference plus cosine of the sum. That is 1/2 the quantity cosine theta 1 minus theta 2 plus cosine theta 1 plus theta 2. So therefore, using the trigonometric identity, the instantaneous power is V sub m I sub m divided by 2 times the quantity cosine theta v minus theta I plus cosine 2 omega t plus theta v plus theta I. Let's assume then, for a learning example, that V of t, our excitation voltage, is 4 cosine omega t plus 60 degrees, and that we've already computed the impedance of the network, and that turns out to be 2 angle 30 degrees. What we want to find now is I of t and P of t. Well, in phasor form, as we saw from the last chapter, I is equal to V divided by Z, and V and Z, of course, are phasors. So that's 4 angle 60 degrees divided by 2 angle 30 degrees. And the resulting answer for the phasor I is 2 angle 30 degrees amperes. That means that, reducing it back to the time domain, I of t is 2, the amplitude, cosine omega t, because we're using cosine reference, that's what V of t was, plus the resulting phase angle, 30 degrees. V sub m then is 4, theta v is 60 degrees, I sub m is 2, theta sub I is 30 degrees. And therefore substitution into the formula for instantaneous power gives us 4 cosine 30 degrees plus 4 cosine omega t plus 90 degrees. Notice that the first term is a constant, 4 cosine 30 degrees is a constant, and the second term, 4 cosine quantity 2 omega t plus 90 degrees, is a time-varying function. We can plot that function of P of t along with V of t and I of t, and this is what it would look like. So notice that the instantaneous power does have a constant term. There's an average value which we can evaluate, but we can see analytically it's 4 cosine 30 degrees. And then we have another component. Notice that the sinusoid that represents P of t is at twice the frequency of either I of t or V of t. Section 2, Average Power. For sinusoidal and any other periodic function, as we'll see, we can compute the averages over one period. So let's define the average, p, as 1 over t, where t is the period, the integral from some arbitrary start point t0 to t0 plus t of the integral of p of t dt. Now we do know that the period t is 2 pi divided by omega, omega being the radiant frequency. Or if you will, the period is also 1 over the frequency. So therefore, we've seen from the last analysis that p of t was v sub m I sub m divided by 2 times the quantity cosine theta v minus theta I plus cosine 2 omega t plus theta v plus theta I. Or, if you will, the average power then, because we want to average that p of t waveform, would just be the first term, which is the constant term. That is v sub m I sub m over 2 cosine theta v minus theta I. And it really results because the second term is time varying, whose average happens to be 0. If voltage and current are in fact in phase, then theta v is equal to theta I. And for in-phase currents and voltages, the average power is 1/2 v sub m I sub m. If voltage and current are in quadrature, meaning at plus or minus 90 degrees, then theta v minus theta I is plus or minus 90. And if you look at the definition for the average power, that means if they are in quadrature, the average power is in fact 0. In the case of voltage and current in phase, that would be a purely resistive network at frequency. And in case of a quadrature representation, that would be a purely inductive or capacitive network at that particular frequency. So here's our learning example. We have a voltage source of 10 angle 60 degrees and a network consisting of a 2 ohm resistor and an inductor whose reactance has already been calculated at that particular frequency, which is not given, as J2 ohms. So therefore I is equal to 10 angle 60 divided by 2 plus J2. And as we've seen in the last chapter, in order to do the complex arithmetic here, we have to take the rectangular representation in real and imaginary parts of the denominator and recast it as a polar form. So that gives us 10 angle 60 degrees divided by 2 to square root of 2 at an angle of 45 degrees. And the resulting current I as a phasor is 3.53 angle 15 degrees amperes. V sub m is 10, of course. I sub m is 3.53. Theta v is 60 degrees, as given in the problem, and theta sub I is 15 degrees, as we obtained in the calculation. So therefore P is 35.3, remember it's the product of V sub m I sub m over 2, cosine 45 degrees, which is the difference between theta v and theta I, and that results in 12.5, and the units of power, of course, are watts. Since the inductor does not absorb power, one can use voltages and currents just across the resistive part, as a common anyway. For example, what is the voltage across the 2 ohm resistor, the only element of the network that is in fact absorbing power? We can get V sub R then by voltage division is 2 divided by 2 plus J2, that is the particular impedance, in this case a 2 ohm resistor, divided by the sum of the impedances of the series network, 2 plus J2, multiplied by 10 angle 60 degrees, that's a voltage divider. And not shown here, of course, we would have to take 2 plus J2 and recast it in polar form, then perform the complex arithmetic. We should do that yourself, and end up with 7.06 at angle 15 degrees volts. That would be the volts that appear across the, as a phasor that appears across the resistive element. Therefore, the power, if you will, if the voltage and current are in phase across that particular element, is 1/2, in this case, V sub R, not V sub M, but V sub R, times 3.53, which is I sub M. And we get exactly the same answer, which certainly verifies that the resistive element is in fact consuming the average power, because the inductive component, a purely inductive real component, does not consume power. Here's our learning example. Determine the average power absorbed by each resistor, the total average power absorbed, and the average power supplied by the source. We have a voltage source of 10 angle 45 degrees, deriving a current capital I into a network which has a single node V, a secondary currents I1 and I2, I1 going through a 4 ohm resistor and I2 going through the series combination of a 2 ohm resistor and a minus J, if you will, or minus J1 capacitor. If voltage and current are in phase, then theta V equals theta I, as we found, and P is equal to 1/2 V sub M I sub M, or if you will, 1/2 R I sub M 1 squared. That would be the current I sub 1 flowing through the 4 ohm resistor, and that certainly would be the case for that 4 ohm resistor, because that's the only element in that particular part of the network. Or if you will, 1/2 V sub M squared divided by R. So therefore I1 would be 12 angle 45 degrees divided by 4, and the result would be 3 angle 45 degrees amperes for I1 as a result. And the power through the 4 ohm resistor, and the 4 ohm resistor only, would be 1/2 12 times 3, or 18 watts. I2 then, as a current divider, can be calculated by the voltage across V, which is 12 angle 45 degrees, divided by the impedance, 2 minus J1. And again, we recast 2 minus J1 as a polar representation. We would perform the complex arithmetic, and the answer would be 5.36 angle 71.57 degrees in amperes. Again, you should verify the analysis and the calculation. Starting with the definition, we can look at just the power consumed in just the resistor, and that would be the power in the 2 ohm resistor, which would be 1/2 2 times 5.36 squared watts, or if you will, 28.7 watts for that particular consumption. The inductors and capacitors do not absorb power in the average. Therefore, the total power is only due to the resistive components, and we would add them. 18 plus 28.7 would give us our total power that we're absorbing, and that obviously must equal the total power supplied. So the answer for the total power supplied is 46.7 watts. We can verify the performance of this calculation. Capital I, the total current, is equal to I1 plus I2. So that would be 3 angle 45 degrees plus 5.36 angle 71.57. Or if you will, I is 8.15 at an angle of 62.1 degrees amperes. Remember that adding polar numbers cannot be done directly. Each polar representation for capital I has to be recast in rectangular form. We would add the real parts and the imaginary parts, and then we would recast the solution back into polar form. Again, you should perform that calculation. P is equal to V sub M I sub M over 2 cosine of theta V minus theta I. Or P supplied then would be 1/2 12 times 8.15 times cosine 45 degrees minus 62.1. And that should be the verification for the actual supplied voltage. That should provide the same answer as we got previously, or 46.7. Again, you should perform that calculation. Another network is a learning extension. We have a 12-volt source at an angle of 60 degrees, feeding a 2 ohm resistor, which then feeds the parallel combination of a 4 ohm resistor and a minus J4 reactance of a capacitor. Find the average power absorbed by each resistor. Well, let's combine the two networks that we see here, 4 ohms and minus J4, and we'll call it Z sub I. And that, of course, is that entire network, which is 2 plus those parallel combinations, 2 plus the quantity 4 in parallel with minus J4, and of course elements in parallel is the product over the sum. We also then will calculate the current that is being driven by that combined network into Z sub I. and therefore calculate that I as a phasor would be 12 angle 60 degrees divided by Z sub I. Here's the calculation. Z sub I for the entire network would be 2 plus the product over the sum, 4 times minus J4 over 4 minus J4. We can put everything over the common denominator, 4 minus J4. We then would have to recast it in polar form, which we can see here. Again, you should verify the calculation. And as a result, we would get Z sub I is 4.47, angle minus 26.6 degrees. Therefore, the current I would be 12 angle 60 divided by 4.47, angle minus 26.6 degrees. And of course, both being phasors, we can do it directly. And the answer for I would be 2.68, angle 86.6 degrees amperes. The power in the 2 ohm resistor then, since that current I flows through the 2 ohm resistor, would be 1/2 R I sub m squared, or 7.2 watts, and that's one of the answers that we need for this particular problem. We then, though, have to calculate I2, because the current I splits into two parts, and the component that passes through the 4 ohm resistor is the desired component in order to calculate the average power. So we need to find I2. Well, we can find I2 using current division. We know what I is, the input current. And the current division is always calculated as the opposite impedance for two elements divided by the sum of the impedances. I2 then is minus J4 over 4 minus J4 times the input current I. We can perform the calculation. Remember to recast them in polar form. And we would get the solution for I2, which is 1.9 angle 41.6 degrees. Again, that's the current we need in order to calculate the power for the 4 ohm resistor. Therefore, the power in the 4 ohm resistor is 1/2 4 times 1.9 squared, if you will. And we now have the power in the 4 ohm resistor. Another learning extension, find the average power absorbed by each passive component and the total power supplied by the source. And we have a 3 ohm resistor in parallel with a 4 ohm resistor in series with a J2 inductor. And it is now being driven across a single node by a 10 angle 30 degrees current source. We need to compute the current, of course, through I1, through the 3 ohm resistor. And that, of course, we do by current division. It's the opposite impedance, 4 plus J2, divided by the sum of the impedances, which is 3 plus the quantity 4 plus J2. Multiplied by the current I, and of course this is just a function of complex arithmetic, which we need to reduce to polar form to produce the final calculation, 6.14 angle 40.62 degrees amperes for I1. The power in the 3 ohm resistor would be 1/2 R I sub m squared. In this case, it's the current I1. Substitution of those numbers gives an answer of 56.6 watts. For 1/2 R I1 squared, if you will. We now need to find I2, which is the current that's going to flow through the 4 ohm resistor and consume average power in that particular element. And we'll do that by current division again. We could certainly do it by current division. However, here's a shortcut. We already know what I1 is, and we also know that I1 plus I2 has to sum up to the source current, which is 10 angle 30 degrees, so why don't we just subtract them? The only problem, of course, is we're subtracting polar representations as phasors, and we need to reduce them to rectangular form in order to do the particular calculation. Or, if you don't want to do it that way, you can do it by current division, your choice. You should get the same answer. So here we have current division, the opposite impedance 3, divided by the sum of the impedances, which is 3 plus the quantity 4 plus J2, multiplied by the input current, 10 angle 30 degrees. Again, recasting them in proper form for the division, we end up with I2 is 4.12 at angle 14.05 degrees. You might want to do the first calculation for I2 is the difference between the two phasor representations and see if you get the same answer. In that case, we now know the current I2, which is what we want. So the power in the 4 ohm resistor is 1/2 4 4.12 squared, or 33.95 watts. And therefore, the other answers, because the problem is asking us for each passive component, which is just a verification of our understanding. The power in the J2 inductor, the answer is 0. Power supplied by the source then is equal to whatever power was absorbed. So we can add the two powers together. We get 90.5 watts. Another method would be to calculate the power as 1/2 V sub m I sub m cosine of the difference of the phase angles. Well, we need to find the voltage that appears across the current source. There is, of course, a voltage because it's across a node. V sub s can be calculated easily since we know what I1 is. It's merely the current I1 multiplied by the resistance 3 ohms. So V sub s is 18.42, angle 40.62 degrees. And the power then is 1/2 18.42 times 10, which is the current, times cosine of the difference between the voltage source V sub theta sub V, voltage source phase angle, and the current source phase angle, which is 30 degrees, the difference. Doing that calculation, we should get exactly the same answer. You might want to perform that to see if you get the same answer, which is 90.5 watts. Another learning example in which we have two sources. The assumption here, of course, is that the sources are running at the same angular frequency, omega, because it's not indicated. So we have a voltage source of 12 angle 30 degrees and another voltage source of 6 angle 0. The network consists of a node with a 2 ohm resistor to ground and a J1, if you will, inductor in series with that 6 volt angle 0 source. So let's calculate I2, which is the current through the 2 ohm resistor. Since we already know the voltage across it, it's set by the voltage source to the left. 12 angle 30 divided by 2 gives us 6 angle 30 degrees amperes for I2. And therefore the power in the 2 ohm resistor, 1/2 R I sub m, in this case I2 squared, 1/2 2 times 6 squared, 36 watts. The power in the inductor, of course, is 0 because it does not consume any power. To determine the power absorbed supplied by the sources, we do need the currents I1 and I2, and I3 also for that matter. So I3 then is can be found because we know what the voltage sources are. We have 12 angle 30 degrees and 6 angle 0 divided by J1, which is the only impedance between those two voltage sources. We can still calculate that I3 is 6 minus J 4.39, or if you will, 7.43 angle minus 36.19 degrees amperes. That's I3. So at this point, we do know a variety of different solutions. We can now calculate the power that is being provided by the 6 volt source, 6 volt angle 0 source. That would be 1/2 6 times 7.43 cosine theta V minus theta I. Well, theta I happens to be negative, so we get cosine 0. That's the phase angle of the voltage source. Minus a minus makes a plus 36.19 degrees. We get 18 watts, which is what that particular power supply is providing. I1 is equal to I2 plus I3. We can perform that calculation. Again, complex arithmetic. We get an answer for I1, 11.28 angle minus 7.07 degrees amperes. And therefore the power in the 12 volt source, 12 volts angle 30, is 1/2 12, 11.28 times cosine theta V minus theta I. Again, theta I is negative, so we get a plus sign, cosine 30 degrees plus 7.07. The answer is 54 watts. And in fact, 54 watts is 36 plus 18, which gives us our verification. Another learning extension, this time with a current source of 12 angle 0 to the left and a voltage source of 4 angle 30 degrees to the right. Network consists of a 4 ohm resistor and a capacitor whose reactance is minus J2. We need to find the average power absorbed by each element. There is a loop or mesh current of I1 flowing in one mesh, and there's a loop or mesh current of I2 flowing in the second mesh. And certainly for the power being absorbed by the 4 ohm resistor, we would need to know I1 and I2. That gives rise, of course, to the voltage across the network, a single node, and that would be the voltage across the resistor also. By loop equations, we know that by definition I1 has to be, it's a constraint, 12 angle 0 because it's constrained by the current source. And we would also get, if you will, 4 angle 30, which is the voltage source. We could then calculate minus J2 times I2, which is the, if you will, the voltage across the capacitor with its reactance, plus 4 times I2 plus 12 angle 0. In other words, the voltage then across the resistor. So that's the so-called loop equations. One is a representation of just the current source. The other one is Kirchhoff's voltage law around that particular loop. Solving for I2, because we do know what I1 is, considers the calculation in polar and rectangular form. As we've seen, we have to reduce it so that we can divide it in polar form representation. Doing that particular analysis with the arithmetic, again, you should check the analysis, gives us 9.97, angle 204 degrees, amperes for I2. We already know what I1 is. So therefore, the voltage across the 4 ohm resistor is 4 times I1 plus I2. We already know what I1 is. It's a constraint. We just calculated I2. Performing the mathematics of complex arithmetic, we end up with 19.92 angle minus 54.5 degrees as the voltage V, volts. There's another alternative procedure, of course. We can use nodal equations, and the single node that we do have, we would have the current entering that single node would be minus 12 angle 0 plus 4 over the voltage across the resistor, V sub 4 ohm divided by 4, plus V sub 4 minus 4 angle 30, voltage source divided by the impedance minus J2. That gives us an equation in which we can solve for I2 and should produce the same answer for I2. And again, you might want to verify that. The power across the 4 ohm resistor, 1/2 its voltage squared divided by the resistance. In this case, 1/2 19.92 squared divided by 4, 49.6 watts. Power across the capacitor, you could say, since it is an ideal capacitor, is 0. The power delivered by the current source, 12 angle 0, is equal to minus 1/2 19.2 times 12 times cosine of the difference of the voltage phasor, theta sub V, and the current phasor, theta sub I. In that case, this happens to be minus 69.4 watts. The power of the voltage source, 4 angle 30, doing the same calculation, gives us 19.8 watts. Power supplied is equal to power absorbed. So basically 19.8 watts should be the representation of the overall consumed power, 19.8 watts and minus 69.4 watts, if you will, which gives us the overall consumed power in the 4 ohm resistor. Another learning extension, we have a voltage source of 24 angle 0 in series with a 2 ohm resistor. We have another voltage source of 12 angle 0 in series with the inductor whose reactance is J2, and shunt across those two elements is a 4 ohm resistor. We're to determine the average power absorbed by each element. We can do this by looking at the node V with respect to ground and doing a nodal equation for the currents that sum into that node, we would get V minus 24 angle 0 held back by the impedance, which in this case is 2 ohms, plus V minus 12 angle 0 held back by the impedance, which is J2, plus the voltage V held back by the impedance, which is just 4 ohms. So we have one equation here and one unknown V. We can straighten it out, end up a linear equation for V. We could then solve for V, and we end up with 14.88 angle 7.125 degrees as a phasor or in rectangular form. We need to find the current I1 because that determines the power that's being absorbed by the 2 ohm resistor. And we can do I1 by noticing that there's a voltage difference across that impedance of 2 ohms as 24 angle 0 minus V, which we just calculated. And it is reasonable to use its rectangular form, which we do have. And we end up with I1 is 4.62 minus J 0.925. Or if you will, I1 is 4.71 angle minus 11.32 amperes. For I2, we could do a similar calculation. In this case, 12 angle 0 minus V held back by the impedance J2. We can straighten out the complex arithmetic and eventually end up with a solution for I2 both in rectangular and in phasor form for I2. The power in the 2 ohm resistor can be calculated. We do know, for example, what the representation is in terms of the voltage across it, and we also know the current through it, so it's your choice about which numbers you do use for the calculation. So let's use the current, 1/2 times the resistor times the current squared. I1 was 4.71. We don't need to worry about the phase angle for I1 because the voltage and the phase are in fact in phase, collinear. So 1/2 times 2 times 4.71 squared is 22.18 watts for the power across the 2 ohm resistor. For the power across the 4 ohm resistor, we can do that in a couple of different ways, but one way would certainly be the voltage across it, not the current through it in this case. So that would be 1/2 the voltage squared divided by the impedance, in this case just 4 ohms. So therefore 1/2 14.88, which is the voltage. Again, not worrying about the phase angle. We end up with 27.67 watts there. And therefore the power from the 12 volt source, 12 volt angle 0, would be minus 1/2 times 12 times 1.67 cosine of the difference in the phase angles, and we get 5.565 watts for the power provided there. And the power from the 24 volt angle 0 voltage source would be minus 55.42 watts. And it is fortuitous because that particular difference does provide the total power being absorbed. So the absorbed power, if you will, is 55.42 watts. I'm sorry, power supplied is 55.42 watts, and if you will, we would produce the same representation by the absorbed power, if you will. This is section 3, maximum average power transfer. In this case, we have a network, which is a Thevenin equivalent network. We see an open circuit voltage in series with some sort of a Thevenin equivalent impedance, ZTH. ZTH would be a complex impedance. It would be RTH plus JXTH. And then that is loaded into a load, which could be a complex impedance, Z sub L. There'll be a voltage across that load, V sub L, and there would be a current through it, I sub L. And of course, Z sub L could also be complex, which would be like RL plus JXL. The power in the load, P sub L, would be 1/2 V sub Lm, I sub Lm, cosine V sub L minus cosine theta I sub L. Or if you will, 1/2 the magnitudes of V sub L, I sub L, cosine of the difference of the phase angles, theta V sub L minus theta I sub L. V sub L by voltage division from this Thevenin equivalent circuit would be Z sub L divided by Z sub L plus ZTH times the open circuit voltage. And I sub L would be V sub L divided by Z sub L. From the first equation, we would get that the magnitude of V sub L would be the magnitude of Z sub L divided by Z sub L plus Z sub H times the magnitude of the open circuit voltage. And the angle of the current, I sub L, would be the angle of the voltage V sub L minus the angle that the impedance supplies Z sub L, or if you will, the angle theta sub V sub L minus theta sub I sub L, or if you will, that would be equal to the angle of the impedance Z sub L. I sub L as a magnitude would be V sub L divided by the magnitude of Z sub L. Z sub L is Rx plus JXL. Cosine theta, this is a trigonometric identity shown in green on the lower left, is 1 plus the square root of 1 plus tangent squared theta. That is a trigonometric identity, which will apply. The tangent of the angle of theta sub Z sub L, the angle of the impedance Z sub L, I should say, is XL divided by RL. Therefore, cosine theta VL minus theta IL is R sub L divided by the square root of R sub L squared plus X sub L squared. And P sub L then can be then analyzed in terms of those terms, which we now have. We have all the terms for P sub L, including the cosine of the difference of the angles, which is the last term, R sub L divided by the square root of R squared, R sub L squared plus X sub L squared. Well, what we like to see is what we can eliminate, and the magnitude of Z sub L happens to be the square root of R sub L squared plus X sub L squared. So those two terms are eliminated from the solution. And we also know that Z sub L plus ZTH is, we add the real parts, R sub L plus RTH plus JX sub L plus XTH. And the magnitude of Z sub L plus ZTH squared would then be the square root of the components, R sub L plus RTH quantity squared plus quantity X sub L plus XTH squared. Substitution of those particular components into the calculation of the load power P sub L gives us 1/2 the open circuit voltage squared R sub L divided by, essentially that same term as a denominator, the magnitude RL plus RTH squared plus the magnitude, the quantity X sub L plus XTH squared. We can now take the derivatives of these particular functions. In other words, the derivative of the load power with respect to the reactance X sub L, the partial derivative actually, the partial derivative because it's a function of more than one variable, and the partial derivative of PCL with respect to the load resistor R sub L, load resistive component R sub L. If you do that particular calculation, what you will find is, in order to meet that particular result, it would mean that X sub L would equal minus XTH and RL equals RTH. This essentially is the formulation for the maximum average power transfer. If RL equals RTH and XL equals minus XTH, the maximum amount of power will in fact be transferred. And therefore, the optimum impedance, if you will, Z sub L, would equal the complex conjugate of ZTH. Complex conjugate would mean that X sub L equals minus XTH and R sub L equals RTH. Therefore, the maximum power transfer in this particular case would be 1/2 the open circuit voltage squared divided by 4 RTH. As an application of the maximum power transfer, let's look at this particular network. The load is called Z sub L. There is an additional network which is part of the source. We have 4 angle 0 as a current source, a 2 ohm resistor in shunt, a J1 ohm inductor reactance, which is then in series with a parallel combination of the 4 ohm resistor and the load impedance Z sub L. And what we need to do is calculate Z sub L for maximum power transfer into the load. We do know that the optimum value for Z sub L would be the complex conjugate of ZTH, and that the power transfer into the load maximum would be 1/2 quantity, the open circuit voltage squared, divided by 4 RTH. To remove the load then and determine the Thevenin equivalent of the remaining circuit, because the remaining circuit represents the source, if you will. So the remaining circuit looks like this. When we remove the current source, we end up with an open circuit. So the network looks like a 2 ohm resistor, a J1 ohm reactance, and another 4 ohm resistor. And we're looking into those terminals, and that tells us what ZTH is. Well, we know how to calculate that because we have a 4 ohm resistor in parallel with the series combination of a 2 ohm resistor and a J1. We can perform the complex algebra, and we have a reduction down to its phasor form, polar form, of 1.47 angle 16.93 degrees. So now we know what ZTH is. However, in order to find the complex conjugate, we should find that particular polar representation and reduce it to rectangular form, which is 1.41 minus J 0.43. At that point, we are asked to find the value of the power, and we also need to know the Thevenin or open circuit voltage VOC. Well, we need to find the current that flows through the terminal J1 followed by the 4 ohm resistor, and that would be called I1, because I1 times 4 ohms would generate the open circuit voltage. So the open circuit voltage then would be the current by division, 4 ohms, times the opposite impedance, which is 2, divided by the sum of the impedances. And the sum of the impedances in this case would be the 2 ohm resistor, the 4 ohm resistor, and the J1 component. So we haven't written it out that way, but 4 plus 2 is 6. Then multiply by the current, because it is a current divider, 4 angle 0, and we get as a phasor representation for the output voltage as 5.26 angle minus 9.64 degrees. So therefore, the maximum power transfer by formula would be 1/2 the magnitude of VOC, the magnitude, which is 5.26 squared, divided by 4 times RTH. And of course, we've calculated RTH as the real part of ZTH, or if you will, the real part of Z sub L conjugate, even, same thing, 4.1, and we get 2.45 watts for the maximum power transfer. Another learning example along these lines: find Z sub L for maximum average power transfer, compute the maximum average power supplied to the load. The network consists, though, of this time of a dependent voltage source. That's what the diamond shape is telling us. V sub x, where V sub x is determined by the voltage whose sign is shown across the 2 ohm resistor, in series with a 4 volt source, 4 angle 0. We have a J4 inductive reactance, and we also have a minus J2 capacitive reactance, and of course a 2 ohm resistor, as we said, with the load impedance Z sub L sitting across the network. Well, we do know that ZL optimum is ZTH conjugate, and we do know how to find the power transfer also. So our task is to reduce the network to its Thevenin equivalent form. But this time we have a circuit with a dependent source, and in that case we need to find ZTH as the ratio of the open circuit voltage to the short circuit current. And that's because there is a dependent source. When there are dependent sources, this must be done in this particular manner. So in this case, let's find the open circuit voltage for this particular network. We can do Kirchhoff's voltage law around this first mesh or loop. Let's do that then. We get 4 angle 0 And again, we have to be very careful about watching the signs and the directions that we're traveling. We're traveling in a clockwise direction. So we get 4 angle 0 is equal to minus v sub x, because it's opposite sign, minus v sub x plus the quantity 2 plus j4, which are the passive elements in the loop, times the current I1, which is in this loop. Remember, it's an open circuit, so that's the only current that flows. And we find Vx then is minus 2 I1 as a result. So substitution then gives us 4 angle 0 is equal to 4 plus j4 I1. And we can now calculate I1 as 0.707 angle minus 45 degrees. We can then do Kirchhoff's voltage law around this particular loop to find VOC. And VOC turns out to be square root of 10 angle minus 165.5 degrees volts. So now we have the open circuit voltage, and we need to find the short circuit current. So the next thing we'll do is we'll short circuit the terminals and determine what the short circuit current might be. So shorting the terminals, we end up with this particular network, removing, of course, Z sub L. We have a current I, and we have a current ISC. We can do loop equations then, if you will. Here are the loop equations for the first loop, minus Vx. And again, we're using the notation double prime because, in fact, the voltage is different than it was in the first analysis because we've now changed the network. But let's just simplify by saying minus Vx plus J4I plus 2 the quantity I minus ISC minus 4 angle 0 is equal to 0. Straightening out that equation and solving, we find that there's a controlling variable, namely the voltage that appears across the 2 ohm resistor, V sub x, is 2 ISC minus I. So we must substitute that. Substitute and then rearrange it algebraically. We're now wanting to find the short circuit current ISC, and as a result, we now have an equation for I in terms of ISC. Substitution and continuing to straighten out the representation, substituting the different terms, we finally get ISC by manipulating the equation algebraically and then reducing it to a phasor form, square root of 5 angle minus 116.57 degrees. In all of these calculations, you should verify that your analysis can proceed in the same manner and end up with the same results. The open circuit voltage we had already calculated, and therefore the maximum power transfer can be calculated because we do know the open circuit voltage. And we do know ZTH as a result, because ZTH is a ratio of VOC to ISC. So we get the representation of VOC then as the square root of 2 angle minus 45 degrees. And of course, we need ZTH in rectangular form, which turns out to be 1 minus J, or 1 minus J1, if you will, because we need to know what RTH is. And RTH we get from ZTH, which is 1. And therefore, the optimum value for the load is the complex conjugate, try 1 plus J1. And the maximum power transfer can now be calculated as 1/2 VOC squared, square root of 10 squared. And it's 4 RTH, but of course RTH is 1, so it's just a 4, and we get 1.25 watts. Another learning extension with 2 voltage sources, 24 angle 0 and 12 angle 0. We want to find Z sub L for maximum average power transfer and then compute the maximum average power supplied to the load. We do know what our processing equations are for those solutions. We need to find the Thevenin equivalent circuit. So we take off the load, we get an open circuit representation, and we need to find the open circuit voltage. In this case, we have a single mesh current I, which we can calculate directly. And we get an equation 36 angle 0 is equal to 2 plus J2 times I. It's 36 angle 0 because the 2 voltage sources have added, and they add in the same sense because they have the same phase angle. You have to be careful about that. and they also have the same sign. So it's really 12 angle 0 plus 24 angle 0 is 36 angle 0, which gives us I is equal to 12.73 angle minus 45. The open circuit voltage then would be the current I through that particular open circuit network, which consists of a minus 12 angle 0 voltage source. It's minus because the sign convention for the open circuit voltage is opposite to that voltage supply, plus J2 times I, in which we get 6 plus J18. And therefore, the open circuit voltage can also be written as a phasor, 18.974 angle 71.57 degrees. And the magnitude squared could be calculated either as 6 plus 18 squared, or 360, or for that matter, 18.974 squared, which should also be about 360. The next part of the calculation is to find ZTH. For that, we let the two independent voltage sources go to 0, which becomes short circuits, and the network is as shown. We have essentially a ZTH looking into those terminals of a minus J2 reactance in series with the parallel combination of a 2 ohm and a J2 reactance. And of course, the parallel combination is the product over the sum, so it's minus J2 plus 4J over 2 plus J2. Performing the calculation for ZTH with the complex arithmetic, we end up with 1 minus J. And therefore, the optimum load would be the complex conjugate. Complex conjugate, of course, is the negative of the imaginary part. So it's 1 minus a minus, which becomes a plus J, or 1 plus J. The maximum power transfer is 1/2 the magnitude of the open circuit voltage squared divided by 4 RTH. And of course, RTH is 1 again. So we end up with 1/2 360 divided by 4 is 45 watts. Here we have another network with the same concepts and the same requirements. We have 24 angle 0 and a 12 angle 0. Please note that the phase angles are the same, so it would be relatively easy to add them. If they're not the same, they have to be considered as complex numbers or phasors. We have a 2 ohm resistor, a minus J2 capacitor reactance, a J2 inductor, and then finally a Z sub L. We have the same processing equations as before. Since there are independent sources, we can provide the normal analysis for the Thevenin equivalent circuit. The open circuit voltage, as we've done before. This time we'll do it as nodal analysis. We'll look at the node which is across the J2 inductor. The voltage across the J2 would be by voltage division. Notice that the 12 volt angle 0 source does not participate in the voltage division. So it's J2 divided by the sum of the impedances, which happens to be J2 minus J2, and they will cancel, plus 2 times 24 angle 0, because the sign goes in the proper direction for that particular source. So therefore the answer is 24 angled 90 degrees as a result. We can do Kirchhoff's voltage law across a simple circuit to find the open circuit voltage, and VOC would then be 12 angle 0, in this case plus 12 angle 0 because the polarity is correct, plus 24 angle 90 degrees, and that polarity is also correct. So we get 12 plus J24 for the open circuit voltage as a phasor, and the magnitude squared would be 720. Find ZTH, let the voltage sources go to 0. The 12 angle 0 doesn't matter because it's still open circuit, but it's a short, of course. And now we end up with this particular network, a 2 ohm resistor in series with minus J2, and then all in parallel with J2. So therefore we get the calculation as the products over the sum. We then straighten it out, and we do end up, after calculation, again you should verify this, as 2 plus J2 for ZTH, and therefore the optimum load, ZL, would be the complex conjugate, 2 minus J2, and the power transfer, we already know VOC squared. In this case, the RTH is 2, so we have 1/2 times 720 divided by 4 times 2, or 45 watts. Section 4, effective or RMS value. RMS stands for root mean square. The effective value that we would have for steady-state AC analysis is equivalent to the DC value that supplies the same average power. So instantaneous power, P of t, as we saw, is the current squared times the resistance. That's one formulation for it. If the current is sinusoidal, the average power then for a resistor is known to be 1/2 I sub m squared times R, or the effective square of the current. The effective current squared is 1/2 I sub m squared. If current is periodic with a period t, then we have the average power is 1/t, the integral from some point t0 to t0 plus t, P of t dt. So we could then substitute the definition that we had, which was R times 1/t, the integral now of the square of the current over the same interval. If the current is DC, then we know that I of t is IDC, and we then reduce to the formula that we're used to from DC circuits. The power is IR squared, or if you will, RI squared. The effective power and the effective current then really are equal. P average is equal to P DC. And the effective current squared then is 1/2 the integral under the period of the square of the current. The effective current itself, not the effective current square, is just the square root of that. So the definition is then valid for any periodic signal with period t, as we'll see, not necessarily sinusoidal, as long as it is, in fact, periodic. For a sinusoidal signal, we know that, for example, the source would be like xm cosine omega t plus theta, and the effective value then would be xm divided by the square root of 2, because that's what we would get if we square the cosine wave and then integrate over a period. For the sinusoidal case then, the average power is 1/2 V sub m cosine, I sub m cosine theta v minus theta I, as we saw in the last section. And the average power then would be V effective times I effective cosine theta v minus theta I. So what we have, in essence, is that the effective power is equivalent to the RMS, the root mean square. And in fact, the concept of root mean square comes by looking at how we calculated the effective current. We square a waveform, we find its mean by integrating over a period and dividing by the period. That would be the mean value, and then we take the square root. So that's why it's called RMS, root mean square. Here's a waveform that's not a sinusoid, in which we're asked to compute the RMS value of this particular voltage waveform. The first task, though, of course, is to consider that, is it a periodic waveform? And we will just assume that it is periodic. And hopefully you could see that the period happens to be 3 seconds, because the waveform repeats every 3 seconds. So XRMS would be 1 over the square root of 1/t times the integral of x of t squared dt. So here's one period, as we said, 3 seconds. Actually, you could take anything that is 3 seconds, but it's convenient to start at 0 if we can, and go out to 3 seconds. We can write an analytical description for this waveform, which is key in order to do the analysis. For a sinusoid, we do know the analytical description, but in case of complex waveforms like this, we have to write essentially an equation which is valid over intervals. So in this case, V of t, a complex waveform, consists of 3 parts. The first part is a linear ramp of amplitude 4t if you will, which is valid over 1 second. We do know that's valid because it meets the requirements of linearity. When t equals 0, 4t is equal to 0. When t equals 1, 4t is equal to 1, and it does agree with the graphics. Then from 1 to 2, it's identically 0. And last but not least, for the last part, we have -4 quantity t minus 2. A little bit harder to analyze, but it's because it's valid over the range 2 to 3. So we substitute t equals 2, we get 0. And if we substitute t equals 3, we get -4. So therefore, it is a correct analytical representation. So now we can compute the integral under the square, the integral from 0 to t of v squared of t dt, and we do that integration by parts. That's why you learned integration by parts in calculus. Integral from 0 to 1 of 4t squared. We don't have to integrate the second interval from 1 to 2 because it's 0. And the last interval from 2 to 3 is the quantity 4 times t minus 2 quantity squared dt. So now it reduces to a problem in calculus. The two integrals have the same value. Well, they are the same waveform, and under the square they would have the same representation of the integral under the square. We could certainly simplify this particular calculation. I don't recommend this as a general rule, but in this case we can simplify the calculation just by doing it once from 0 to 1 and then multiplying by 2. So 2 times 16 over 3, because t squared over 3 would integrate to t cubed over 3, of course, by calculus. Evaluated over the definite integral from 0 to 1 with limits is 32 over 3. So VRMS then, by this particular calculation, we know the period is t, so it's the square root of 1 over t times what we just calculated under the integral squared, which is 32 over 3. So 1/3 of 32 over 3, and we get 1.89 volts as the RMS value. And it's also reasonable because it's within the range. We didn't end up with a number in the thousands of volts. It's within the range, so certainly a reasonable number for that graphical representation. Here we have another waveform, which is periodic but not sinusoidal. Compute the average value of the voltage waveform and use it to determine now the average power supplied to the resistor. Well, in this particular case, we have a waveform which has a period of 4 seconds. We can see that clearly. If we square the waveform, it becomes a constant. In fact, I squared of t is nothing more than 16. You should verify that in your own mind over the range from 0 to 4. Because when we square the waveform, minus 4 becomes plus 16, and of course 4 becomes 16. And therefore IRMS is the square root, and IRMS is 4 as a result. The average power is R times IRMS squared. In this case, a 2 ohm resistor, IRMS squared gives us 32 watts. XRMS is, of course, the square root of 1 over t, the integral under the square over a period. And we can get the answer conveniently using the standard definitions. Another example, triangular waveform. Find the RMS value of the voltage waveform. Key here, of course, is finding the period. Period is also 4 seconds in this case. We have a calculation for XRMS. We have a period of 4 seconds. We can write an analytical description for the waveform. It's V is equal to 2t, because in 2 seconds it rises to an amplitude of 4. And of course it's 0 otherwise. So in this case we don't have to integrate from 2 to 4. We can integrate from 0 to 2 of the analytical expression 2t quantity squared. And the period is 4. Please note that the period is 4, not 2. So 1/4, the integral from 0 to 2 of 2t squared dt is VRMS. And performing that calculation, we get 8/3 of a volt, which again is reasonable. Another example, compute the RMS value for this current waveform and then determine the average power supplied to the resistor. So now it's a current waveform. And the difference here is, of course, we don't have zeros, but we seem to have constant values, and then it changes to another value over another constant period. So we need to write an expression and apply our standard formulations. We have resistive loads of 4 ohms. So we notice that the period is 6. You have to verify that in your own analysis. The period is 6, means that if you take any 2 points on the waveform, it repeats every 6 seconds, and we can conveniently start at 0. We can then write the equation for IRMS squared as 1 over the period, which is 1/6. We can integrate from 0 to 2. It's a constant of 2, so we square it, we get 4. We can integrate then from 2 to 4, which is a constant of 4. We square it, we get 16. And don't forget the last portion. We integrate from 4 to 6 of a constant of 2. We get 4, and that is our integration, whose answer turns out to be 8. And therefore the power is, that's for IRMS squared, Therefore, the power is IRMS squared times R. 8 times 4 is 32 watts. Another representation here now with R equals 10 ohms, following the same concept. We have a period of 8 seconds. In this case, we have zeros, so we can ignore those particular integrals, but please remember that the period is still 8, so we get IRMS squared is 1/8. The integral from 0 to 2 of 4 squared is 16, and then we have a 0 element from 2 to 4. Then we go from 4 to 6, and it's minus 4, but when we square it, it's also 16. And of course, the last element from 6 to 8 is 0, and therefore IRMS squared is 8. And therefore, the power is IRMS squared times 10, which is 80 watts. Let's consider now something called the power factor. When we have a current I sub m at some angle theta I into a load impedance Z sub L, which then produces a voltage V sub m at some angle theta V, we can now define its vector relationship, for example, theta I for the vector or phasor representation of I, and another vector or phasor representation of V. And we now have the voltage V is equal to Z times I. So that's a phasor calculation, of course, but the angle of the voltage V is the angle of the impedance Z plus the angle of the impedance I. Or if you will, theta V is equal to theta Z plus theta I. So theta Z, if you will, is the difference between V and I as an angle, theta Z. Current leads in this particular case, if it's capacitive, we saw that in chapter 8. If theta Z is between 0 and minus 90, it tends to be a current leading situation, capacitive. If theta Z is between 0 and 90 in the opposite sense, we call that a current lagging, or so-called inductive current. Here P, the power P, is 1/2 V sub m I sub m cosine of theta V minus theta I, which we've seen in the last section. But it could also be written as VRMS times IRMS cosine theta V minus theta I, if you will. The apparent power then is VRMS times IRMS, and we'll discuss what the apparent power is. It's basically just the product of the two magnitudes without the phase angle. The power factor then is the power P divided by the apparent power. And what we're left with is merely the cosine of the difference of the angles, theta V minus theta I, or if you will, cosine theta Z. And that's what is known as the power factor. The power P then is VRMS times IRMS times the power factor. So the power factor is a convenient way of showing the relationship between VRMS, IRMS, and the apparent power. So power factors take on a range. If the power factor is 0, then theta Z is minus 90. That means purely capacitive. If the power factor is between 0 and 1, we know that we can have minus 90 to 0. That would be leading or capacitive resistive. And because of the nature of the cosine function, if the power factor is 1, we end up with a 0 degree resistive case. And if the power factor is also between 0 and 1, we can have a lagging or inductive, pure inductive. And the reason why we have those two different ranges, which look similar for the power factor always going between 0 and 1, is because cosine is an even function. Cosine theta is equal to cosine minus theta. So here we have our learning example. Find the power supplied by the power company. Determine how it changes if the power factor is changed to 0.9. So here we have a problem in which we have the load power, P sub L, is 88 kilowatts. The power factor is 0.707 lagging. We know that the voltage then is 480 volts RMS. We know the power company provides V sub S with an apparent load resistance of the source of 0.8 ohms. And we want to now analyze this particular practical problem. Well, cosine theta then is 0.707 because that's what we mean by lagging, and we get minus 45 degrees because the lagging tells us it's minus 45 degrees. Remember, the cosine's an even function. P is equal to VRMS times IRMS times the power factor. We're told what the power factor is. Therefore, IRMS is 88 kilowatts, 88 times 10 to the third watts, divided by 480, which is the voltage RMS, times 0.707. So we've applied the power formula, if you will, and solved for the unknown IRMS, which gives us 259.3 amperes RMS. The power losses then are IRMS squared times R, because that's unfortunate, but that's the power loss because of the 0.08 ohm in series. So it's 293.3, in this case squared, not cubed, times 0.8, and we get 5.378 kilowatts, or if you will, 5,378 watts. Please observe the units when you do the calculation. The power from the source then is power plus the losses plus the power in the load, which is given as 88,000. So we end up with 93.378 kilowatts, if you will. 88,000 is 88 kilowatts. If the power factor, though, changes to 0.9, how does the answer change? Well, we recalculate the IRMS value because the load remains the same. We get 203.7 amperes RMS. The power losses now, IRMS squared R, is 3.32 kilowatts. And if we can change the power factor, the losses can be reduced by 2 kilowatts. It should be noted that the power company really charges you for the power that they supply, which is 93 kilowatts. Okay, so let's take a look at the generated voltage under these conditions. We know that current lags the voltage. Therefore, 480 volts RMS and 259.3 at angle minus 45 degrees. And the first condition would look like this, red being the current and blue being the voltage. V of the source RMS would be 0.08 IRMS plus the voltage across the source, which we can then calculate. And we get V of the source RMS is 495 angle minus 1.7 degrees. And if the power factor is 0.9, we find that the calculation then changes. You should verify this. And we get 494 angle minus 0.82 degrees. So essentially the voltage from the generating source will actually slightly be lowered if we can increase the power factor. Not only will our losses be lower, but the power company will be much happier providing less V sub S than it did before. In this learning extension, we have an industrial load consuming 100 kilowatts at 0.707 power factor lagging. The 60 hertz line voltage is 480 angle 0 degrees RMS. The transmission line resistance between the power company transformer and the load is, in this case, 0.1 ohm. Determine the power savings that could be obtained if the power factor is changed to 0.94 lagging. I will say at first that there are some incorrect numbers being inserted into the problem, and the calculations seem to be right, but the numbers are wrong. So you might want to verify this as we go along. This seems to be right. Cosine theta equals 0.707. That means theta z is minus 45 degrees because it's lagging, and current lags the voltage. This calculation is wrong because we do know that the P sub L is 100 kilowatts, not 88. So it should actually be 100 times 10 to the third upstairs, divided by 480 volts RMS times 0.707. The number, in fact, is right, 297.67 amperes RMS. The losses can be calculated as IRMS squared times R, and certainly it is 294.67 squared, but it's multiplied by 0.1, and those answers are right, not 0.08. That was the last problem. So therefore, P sub S is P losses plus 100 kilowatts. That seems to be right. Gives us 108.3683 kilowatts total. If the power factor is raised to 0.94, now we have the right numbers. ISO RMS is 100,000 divided by 480 times 0.94. We get 221.63 amperes RMS, and the losses are IRMS squared times R, and that is correct with 0.1 ohms. We get 4.912 kilowatts, and if we can raise our power factor from a miserly 0.707 to 0.94, we can reduce our losses by 3.771 kilowatts, and I will tell you that the power company bills you essentially for those losses by not having a power factor that is large. With that, we have the end of Chapter 9, Steady State Power Analysis, Sections 1 to 4. There are additional problems in the text. You might want to look at those problems and consider them for class discussion.